So first of all, let me thank all the organizers for the opportunity of speaking here. And so, today I'm reporting on this on a joint work together with Joachim Jelisheyev, Pedro Maches-Marx, and Christian Ranestad. That it's about the Cactus variety of cubic forms. In particular, I will show you a theorem on the dimension of the Cactus variety of cubic forms. And I will underline in particular the idea of the Apolar scheme Artinian Gorenstein rings. Okay? Apolar local Artinian Gorenstein rings. So, this work? Okay. So I will start with a brief introduction. I mean, since Jarek gave already a big part of this introduction, so I will recall the Warring rank and the Cactus rank, what they are, and then I state the theorem. Then I need few tools. One is the Apolarity that Jarek already said something, but also some days ago I think Enrico presented it. And then I have to also say what a local Apolar scheme is, and then I can go into the detail of the proof of the theorem. Okay, so for me, f is an homogeneous polynomial of degree d, and the field has to be algebraically closed, and they just need that the characteristic is not 2 or 3. I mean, this condition won't ever show up in the whole talk. I just put it because we need it in the theorem, because we use another theorem where there is this condition, but we will never use this. So what's the Warring rank? Once again, we have an homogeneous polynomial of degree d, and the Warring rank is the minimum integer r, such that f can be written as a sum of r pure powers of linear forms. Okay? So that's the Warring rank, and that's the definition. So I want to rephrase this definition by using the Veronese map. The Veronese map, it takes a linear form and is sent into its pure power. So the image of this map is the Veronese variety. So every point in the Veronese variety is a pure power of a linear form. So saying that f can be written as this linear combination means that our f is in the linear span of r points in the Veronese variety. So it belongs to an r secant space to a Veronese variety. But it means also that here, so the Veronese map starts from linear forms and go into polynomials of degree d. It also means that in the space of linear forms, I have r points that are sent in these r points here whose span contains my f. So a complicated way of saying this is that there exists a scheme, finite, so points, smooth, so simple points, of length r, so they are r points, whose span, whose Veronese image and the span and f is contained in the span, okay? So for me, every time I say scheme, you have to think a scheme as set of points, and every time I say smooth, it means there are simple points. So now what I want to do is to remove the word smooth from this definition. And if I remove the word smooth from this definition, you already know from the previous talk, you get the definition of Cactus rank. So the Cactus rank of f is a minimum r such that there exists a finite scheme in the space of linear form that is sent by the Veronese variety in another scheme here whose span contain f. So what's changing is that my points now are not simple anymore. I mean, they're not distinct points, but I can have multiple points on each support. I put here in the bracket the word Gorenstein, but I don't need it in the definition. It will turn out that they are Gorenstein, but we will come back on that. So now, if I look at the variety parameterizing all the polynomial of rank r, I get the secant variety of the Veronese. And here I have this word smooth, and as I said, if I remove the word smooth, I get the Cactus rank. And so if I take the same definition, removing the word smooth, I get the Cactus variety of the Veronese variety. So the Cactus variety is the closure of the union of all the span of this needy gamma, where gamma is a scheme of length r, and that's it. Okay? Okay. So what I want to prove what I want to show you is the dimension of this variety in the case of degree 3, when the Veronese embedding is 3, is cubic forms. Okay? So, okay, we focus on cubics, and the theorem that I want to prove is the following. That whenever R is the length of the scheme, is smaller or equal than 17, these two varieties are the same. Clearly, by the definition of the secant and the cactus, I mean, since from this definition I remove the word smooth, this variety is contained in this variety.
The cactus variety is irreducible?
No.
Hilbert scheme isn't.
Okay. Then go back to the next slide. Sorry.
So, whenever the R is more or equal than 17, these two varieties are the same.
That's what GM is questioning. He's saying that if you don't know that...
I'm sorry, the dimensions are the same. Okay.
So they're not the same?
They're not the same, yes.
Necessarily?
Yeah.
Okay.
Thank you. Yeah. The dimension of these two varieties are the same. Okay, good. And for this, we actually had to care about for R bigger than 13, because for R smaller or equal than 13, there was already a paper, I mean, it's a preprint of Kasnati, Notari, and Yelisheyev, where they show that any local scheme is mutable if R is smaller or equal than 13. And, am I right?
Local Gorenstein scheme.
Local Gorenstein scheme is mutable. Yeah. I didn't take care of this because in my talk everything is Gorenstein. Sorry. Yeah. So in our case we have to take care only for R bigger than 13. And if R is 2n plus 2, then the cactus is going to fill the ambient space. And if R is in between 18 and 2n plus 2, then we have a strict inequality here.
Sorry, no, I know you want to sweep this under the rug, but so is it that you can restrict attention to Gorenstein schemes, or that these things are automatically Gorenstein?
These things are automatically Gorenstein things, yeah.
Okay.
You take minimal, then they are automatic. Mm-hmm. You have to take minimal one, then you are...
The minimal ones are always Gorenstein. So if you choose wisely, you're always Gorenstein.
Yeah.
Okay. Sorry.
And this is a dimension, okay? Okay. So I need some tools. The first one is Apolarity. So what's Apolarity once again? Apolarity is a sort of duality between two spaces of polynomials, S and T. And I want to think T as the partial derivative on S. So I want to act T on S as the partial derivation, almost as partial derivation. As you see here, I don't have any coefficient. So I'm using the divided power ring. This is only because of that condition of characteristic to not to be 2 and 3. But I mean, if you are thinking to your favorite complex numbers, it's fine even if you take the standard partial derivation. And so with this action, the degree 1 part of these two spaces, they are dual spaces to each other. And I can think T as the naturally coordinate ring of PS1. So now I give two definitions. One is the apolar ideal. So if I have a polynomial f in S, I define the apolar ideal to be what? To be the perp via this action. So the set of all partials, so it sits here, the set of all partials that vanish, that when I apply them to f, I get 0. And I also define the apolar scheme to f, an apolar scheme to f. So gamma is inside PS1 and is apolar. It's a scheme and is apolar to f if its representing ideal is contained in f perp. So with these two definitions, I can say rephrase the apolarity lemma that Enrico told us yesterday. And I can say that the scheme is apolar to f, to a form f, if and only if f is contained in the linear span of its Veronese image. So now you see, with these two definitions and this lemma, I can rephrase the definition of cactus rank. And I can say that, so we said that the cactus rank was the minimum R such that there exists a scheme here such that f belongs to the span of its Veronese image. But for what we said of the polarity lemma, this is the same thing of saying that gamma is apolar to F. That's the same thing by definition of saying that the ideal of gamma is contained in F perp. Okay. So these are the tools of the polarity that I wanted to show, and then now we pass to the other tool that are local apolar scheme. So if I look at this ring, I look at T over F perp. So these are partials. These are the partials that vanish on F. So these are the partials of F, actually. It turns out, this is proved by Yarobin and Kanev, that it's local Artinian Gorenstein. And so what I want to stress is the fact that it's local. The fact that it's local means that it's supported at some points. Okay? So I have my F. I look at the minimal apolar scheme. I know that it's locally Gorenstein. Locally means that it's supported at some point. I have this gamma I, so each of these gamma I is supported at one single point. So it means that my F, in general, is in the span, the black one, of both, here I took just two points, but of the scheme, is in the span of this scheme. But also I can find a polynomial in the span of each one of these, such that their combination gives capital F. But I can be even more general. So, in fact, any local Artinian Gorenstein scheme is the affine apolar scheme to a polynomial G. Okay? Meaning that for any local Artinian Gorenstein scheme, okay, here I'm taking the affine space, there exists a G that is affine such that the ideal where I'm quotienting by, it's the perp of that G. Okay, so I have my F. My F defines certain gamma as the minimal local Gorenstein scheme, blah, blah, blah. Gamma is supported on points, local. And gamma, I've just said, that is defined by affine polynomials. Each of these gamma i's is defined by affine polynomials. So the first thing that I want to do to prove this theorem is to understand the link between the F and the GI's. Okay, now I want to understand this link. So G now is not homogeneous anymore. I'm going to call, so this is the degree 0 part of G, this is the degree D part of G, dd plus 1, and so on. I'm going to call its lowest degree D part the degree D tail of G. And the link between capital F and the GI is showed by this proposition. So I have my polynomial F of degree D. I dehomogenize it by some linear form. Now I've taken x0, but I can take another linear form. And then I let gamma be a scheme of minimal length among those that are supported at the linear form that I've used to dehomogenize F, the same one, that are apolar to F. Okay? Maybe it's not the minimal apolar scheme to F, because I want that is supported at L. Maybe it has a bigger length with respect to all the apolar scheme to F. But among those that are supported at L, I'm taking the minimal one of the minimal one. So gamma, we have already said, is the affine apolar scheme to a polynomial G. That is affine, and the fact is that G has the same degree, the degree detail of G is exactly F, small f, the dehomogenization of capital F by this linear function. Okay, so clearly this G is not unique, but this is saying that I can choose G in such a way that, there are many G's that defines gamma, but this is saying that I can choose G in such a way G has the same degree detail of F. That the degree detail of G is F. So just the idea of the proof of this proposition. So first I want to define what I call the natural apolar scheme of F at L. So as I said, I can have many polynomials that are apolar to F supported at L. But is there some one of them that is natural? So I call it natural, this one. So I dehomogenize my capital F, I take the perp of small f, and I look at the zeros of that. So this is the natural Polar scheme of f at L. So then we have this lemma for which we have to thank Jarek for this. We were stuck for some point at this, at this level. So if we have a local scheme supported at L that is Apolar 2f, there always exists another scheme, or maybe the same, but there always exists a scheme contained in Z that is Apolar 2f, such that our Z prime, the new one, is the natural Apolar scheme of some G, capital G, where G has this relation with F. So F is the partial of G. So this says that we can choose our gamma, the gamma that we are looking at, to be the natural Apolar scheme of some G. Then, if we have this, if F is a partial of G, then we look at the dehomogenization. One can show that these two guys have the same degree detail. So this phi G is going to play the role of the G in here. Okay, so this phi G is our G. And I mean, it's quite easy to show that Z phi G is contained in gamma, and that is a polar 2f. Okay, so now we have this proposition that tells us the relation between the f and the GIs. So the GIs are, each one of the GIs, each one of the GIs is supported on, I mean, it defines the scheme that is supported on different points, and they have the same degree detail of small f, but small f is different for every point because I have to dehomogenize f for independence on the point where I'm localizing it. Okay, so the next thing to do that we have to do if we want to find the dimension of the Cactus variety is that now we want to parameterize all the polynomial G whose affine Apolar scheme has certain given length.
So up until now we have nothing about degree 3.
No, nothing.
Okay. Sorry, but the theorem is about degree 3.
Yeah. The theory is all about degree 3. I mean, these things are gonna. I mean, there's nothing that tells us that is not gonna work for any D except computation.
Okay, that's good. I'm missing something.
Yeah, I'm not using. I'm just we did it for degree 3 because then the complexity of the computation is really growing. So by our proposition is the same thing of parametrizing the family of cubic tails f of some G's. So what am I saying? So this CRL is, so I fix L in the Veronese variety. I look at all the schemes of length at most R supported at L. I take all the span of them and I take the union. Okay. So this by the proposition above. By the previous proposition is the same thing of looking at the forms that have fixed degree detail with certain number of partials, and then we will take the union of this CRL by varying L in the linear forms, and then the Cactus variety will turn out to be the closure of the union of the join of all these WRI, where the sum of the RI sum up to R. So what I want to do now is to parameterize the set of this polynomial. And that I've just said is I want to parameterize the family of cubic tails f of G. In order to do that, I want to find an invariant for local Artinian Gorenstein schemes that parameterize the cubic tails, now I'm passing to cubic, of polynomials that define a scheme with that given invariant. And if I can find that invariant, I want to find also which is the one that defines the biggest family. I mean, I don't want to compute all those dimensions. If I can find the biggest one, I'm fine. And I can anticipate that invariant will be the Hilbert function equipped by a symmetric decomposition. So I rephrase once again this isomorphism. I've already said it, but I need it. So T is the space of partials, and these are the partials vanish on F. So this is actually the space of the partials of F. And I'm going to use this isomorphism because I want to interpret a work of Jarobino. So Jarobino showed that this TF is local, that is one maximal ideal. And so it took two different filtrations in TF. One is the degree D filtration, sorry. And
Can you show the previous slide again? Too fast for me.
Sorry. I rewrote the same things many times.
It's going very fast.
I'm going fast?
For someone like myself, maybe for experts, it's not too fast.
I'm fine. I don't know how to deal with it.
Okay.
Okay, so now I look at this ring. I want to take two different filtration. One is the degree filtration, and the other is this low AOE filtration. If I don't have any assumption on F, they are different, these two filtrations. And by that isomorphism, I want to interpret these two filtrations in terms of filtration of order filtration and degree filtration. In fact, if I take the maximal ideal, the degree ith power of the maximal ideal is sent by that isomorphism into partial of order at least I of F, where the order of a partial is the largest order of some partials, such that the order of partial F prime of F is the largest order, such that F prime is that phi of F. While this low AOE ideal is sent into the partial of degree at most I minus 1 of F by that isomorphism. So I can rephrase these two filtration, this one and this one, by using filtration on the order and the degree. So I have an order filtration and the degree filtration. They are the same as before by that isomorphism. So since F is not homogeneous, those two filtrations are different. But if I look at successive quotient, I mean these two quotient, they are isomorphic. I'm just saying that. So I have this isomorphism in terms of the order and the degree filtration. Now, if I take, this is just a notation. This is the partial of degree at most I and the order at least D minus I minus A. So I look at those quotients. It's kind of difficult to read here, but you'll understand why I'm doing that. So this is the partial of order of degree at most I and order D minus I minus A, and these are the others. So I switch the role of I and A, and I quotient by these two things. I get this isomorphism. Why I'm saying that? Because this isomorphism allows us to say that the Hilbert function of the two filtrations, so I have two different filtration, I can associate two different Hilbert functions, but because of this isomorphism, those two filtration are dual to each other. That means that our Hilbert function, now I took the one of the degree, but I could have taken also the one of the order, it has some symmetric decomposition, where this delta A are exactly the dimension of these spaces here. And this turns out to be symmetric around this value. Okay, let me see in an example what I'm doing, okay, because here we get crazy. I take a simple example. My F, as I said, is not homogeneous anymore now. And this is a polynomial in two variables, degree 3. I take all the partials of this polynomial, and as you see, I have in degree 0 I have only one. Okay, it appears twice, but I have only this one. In degree 1 I have x1 and x2, and this is this 2. In degree 2, I have x1 square, and this is this one. And in degree 3 I have only f, that is this one. So this is our Hilbert function. Now, I said that I want to give a symmetric decomposition of this Hilbert function. And this is the following. This is the symmetric decomposition. So this row is symmetric around its middle. And this row is symmetric around this one. In general, when you have longer Hilbert function, you get something that it is on the anti-diagonal is 0 below, and the rows are symmetric around their non-zero part. Okay, and so which is the meaning of these two rows? You can see this from these two. So you see this two is split in 1 plus 1. And this is because this 2 was because we had 2 forms of degree in the partial. We have 2 guys of degree 1. But one comes from a partial of order 1, and the other one comes from a partial of order 2. Okay? So, I mean, it's more complicated than that because, as you see here, I have quotients, so I have to look at the partial of order and degree, blah, blah, blah. But just to have an idea. So, here is not only the degree that is playing a role, but also the order of the function. So, this is our invariant. The invariant that we are looking at. Not only the Hilbert function, but also this symmetric decomposition that takes care also of the order of our partial. So the next step is to characterize the polynomials f with the given symmetric decomposition for the Hilbert function. So I want to fix the symmetric decomposition of the Hilbert function. I want to characterize the polynomial with that symmetric decomposition. So I'm saying that if I take a general cubic form with even local Cactus rank of rank, so even in rank, I can always write it in this form where F3 is the degree 3 part of F without x0. Okay, so x1 and xm minus 1 are the variables that appearing in this F3, and they are what they are. And then here I have x0 times something of degree 2, and this something of degree 2 is always a product of a linear form in the same variables of F3 and the form in any other variable, a linear form in any other variable. Then I have x0 squared times 1, and F1 can be any linear form. And then I have x0 cubed times the constant.
So F2 is a product of linear forms or a sum of products?
Once again?
F2 is a product of linear forms or a sum of products? Linear forms.
I mean, this is a product of linear forms, yeah.
It always factors.
I'm just saying that it's projectively equivalent to this. I mean, I can always arrive there. And so one can count the dimension of this guy, and it has codimension n minus 1, choose 2 plus 1 in the space of cubic forms. And I can do the analogous for the odd case. And in the odd case, it turns out I have the same guys, this F3, x0 squared F2, and this last part, but I also have these two guys, that is xm times x1 squared, and x0 times xm2 squared. And I can also count the dimension of these forms. Okay. So, yes. So now we want to show which invariant. So this was to. So these two slides, this one and this one, were to show this characterization. So fix the Hilbert function, I can always arrive in these two situations, either this or this one in the even case or in the odd case. Now I want to show which invariant have the biggest family of cubic tails. So I have my CRL that once again is the, so I fix the support L and I take all the scheme of length that most are supported at L and the span of those scheme, the union, they parameterize the family of cubic tails of F. And by the proposition we add, this is the same thing of this set that are the forms of fixed cubic tails and certain number of partials. And now I'm going to split this by fixing the Hilbert function decomposition. So I'm going to write this as the union of all those sets that have fixed degree 3 tail, this number of partial, and fixed Hilbert function decomposition. And I want to look which one of these have the biggest, attains the biggest dimension. Okay? And so the biggest dimension for this will give an upper bound for this, for the dimension of this space here. That's the same of this. And then, so the guys that gives the biggest dimension are the following. One, for the even case, the Hilbert function decomposition is simply this one. So 1, n minus 1, n minus 1, and 1. While for the odd case, the Hilbert function decomposition that gives the maximum is this one. So I have a bunch of ones, and then I have this decomposition here. And these are the dimensions. I'm not going into the details of these numbers. So I have this value, that's the maximum now. This is the maximum, and so now you understand I'm almost done. So the cactus, we said, is the closure of the union of the join of this WR, where the WR, where the closure of the union of the CRR, these are those with the support on the same linear form. And I wrote them as the union of those with a fixed Hilbert function. We found the maximum for this set, and this provides an upper bound for this dimension. So the largest component, for example, in the even case, is the union, as L varies, of this projective variety whose affine corner is isomorphic to this V to V to M, because it's even the even case. So a parametrization of these guys is this dimension minus 1 plus n. Okay, the same dimension of this minus 1 plus 1. And similarly for the odd case. But now one has a problem, and the problem is that the parametrization may not be generically finite. So this formula can give only upper bound for the dimensions. So one will have to show that they are actually one-to-one, that the parametrization are one-to-one. So it turns out that when B is even, that when we are in the even cactus rank, there is a unique linear form that I look as a support, such that the natural Apolar scheme of F supported at that linear form has precisely the length that we are looking at. While in the odd case, we can't say the same, unfortunately, but we can have a polynomial of degree 4 whose partial, in the odd case, there is a unique L again, such that F is the dehomogenization, and the dehomogenization of F, is the degree 3 tail of a quartic polynomial, whose natural Apolar scheme has fixed length. So this actually means that for the even case, if we want to compute the cactus rank, we can always find some L in such a way that the local cactus rank computes the cactus rank. Because the natural Apolar scheme is going to play this role, and I'm also saying that it's going to play it for a unique L. While in the odd case, we have to look at the scheme, the natural Apolar scheme to a quartic that is not I'm just saying that there's no natural Apolar scheme to F that plays this role, that allow us to compute the cactus rank via local Apolar scheme. So, okay, here we are done, because now if the parametrization is generically one-to-one, then I can actually say that these two dimensions are the same, and then I can go through all these procedures. Since I compute all this maximum, I can go back and compute all this dimension and get the dimension of the Cactus rank. And that's it.
Plenty of time for questions.
Could you go back to the slide, the statement of the theorem? It was kind of, So, for example, do you know what the components of the Cactus variety are in the example?
No, I mean, we just focus on the dimension.
You know the smallest example where there is a second component?
Yeah, that's
What's the smallest? So this situation, x3, and what's the smallest r? What is it?
Once again?
What is the smallest value of r between 14, say, and 18? So if you go up 14, 15, what's the smallest r where there is actually a second component?
Of the Cactus rank? Of the Cactus variety? I mean, I don't know. I mean, we don't study we just focus on the dimension. We don't. I don't know.
Do you know for sure that there are other components?
What do you mean
Your
other?
dimension computation, you
Well,
get by
there's the-
parameterizing it, right?
So when
Yeah.
R is less
So
than
you'd be wanting to have-
17, they have the same dimension.
Yeah.
So one component, the secant variety is irreducible. So I'm asking, or we're trying to ask, when is the first case where we know for sure that there's something in the Cactus variety that's not in the secant variety? Or do we have to wait till we get to 18 to be sure?
Well, the dimension calculations come from parameterizing it, so you could ask if the base of the parameterization has more than one component. That would be the start. I couldn't follow what was going on though.
Basic parameterization is very amazing.
I mean the weak.
But it just has L purchase.
But I see for R equal 14, you have the difference.
So if you ask just for the base, there are Gorenstein non-smoothable things below 18. But it's not easy to say if the secant is not like, I mean, if their spans are not contained in other secants.
So for 14, there are non-smoothable Gorenstein schemes, but we do not know whether they spawn off a new component. Is that correct?
If they span a new component, then the component is small. And it's not clear whether the other thing is contained in the big component.
But that's okay, even for the Hilbert scheme of points. If you have 8 points in 4 space, the extra component is lower dimension.
Yeah, but there is a good reason for that.
Do you have a question?
Yeah.
You're saying there's not a good reason for this?
Well, no, I'm saying that we don't understand whether they are different or not.
So Jarek also can prove that when this 3 is a bigger number, then these other components appear.
So I just want to clarify my understanding here. So this Apolar scheme, is that the same as the Macaulay inverse system? The Macaulay inverse system?
Yeah, is the Apolar scheme. Is the Apolar scheme.
So for fixed degree D, does the set of polynomial correspond to the Gorenstein scheme of a fixed Login?
For a fixed degree. Sorry, once again.
So there's a correspondence between polynomial of degree D and Gorenstein scheme of Login D plus 1. Is that true?
Polynomial degree D and Gorenstein scheme of length.
Login D plus 1. So MD plus 1 is 0.
So yes, I think. Yeah.
That's your...
Yeah. Yeah.
But you don't control the dimension of the differential from just the degree.
Yeah.
So I have sort of a philosophical question. You start with things that are homogeneous and you decompose the sums of powers of linear forms. Everything is homogeneous, but at some point you decide to dehomogenize.
Yeah. It's
I mean, it doesn't matter which way you dehomogenize, but still there is some sort of arbitrary choice of dehomogenization. But is that necessary? I mean, somehow it feels, it always feels that the projective space is better than the affine space, but then at some point here you decide to go into the affine space.
Yeah, that's one of the main points. I mean, because we have local schemes. That's the fact that the ring, the TF perp, is local, so it's supported at some points. And then if I want to work locally, it's better to work affine. I mean, that's the main.
So all finite schemes are affine.
Right. The philosophical response, I think, is that you want to always work infinitesimally if you can, and so she was working infinitesimally.
I mean, also you could work with the barrage, but then that's harder to work with.
Yeah, I mean,
I think Max Boggi has an interpretation that you can do everything without the homogenization.
Mm-hmm.
But if you read that at the end, it is more complicated. So I think.
I mean, the idea comes from the fact that that scheme is local, so it turns out to be natural to look at the affine things.
From this, you can say what's the general Cactus rank of a cubic form, I think.
You can say which is the rank, which is the Cactus rank of a general form. Yeah, the one that fills the ambient space. That is, there's 2n+2.
Oh, that's the.
Do you know the general Cactus rank for the cubic tensors?
No clue. I mean, for that, I mean, you have to use. I mean, here apolarity is a kind of important thing. If you pass to tensor, not symmetric one, you have to use a complete different notion of apolarity, whatever it means, in the not symmetric case. So the algebra, as Jarek said before, is completely different. We don't.
Ask one more elementary question. There's a third notion, namely the variety given by the rank constraints of the Hankel matrix.
Mm-hmm.
How does that fit in? Can you just remind me how that? So if I have the Hankel matrix or catalepticum and impose the rank constraints, how does that fit in this situation?
So the Cactus rank is actually. I mean, the anchor rank is going to give you the Cactus rank.
So the Hankel determinantal variety, how does it fit into this slide?
I think the Hankel determinantal variety is fewer conditions than the Cactus rank.
So it's even larger.
Yeah.
So secant contain the Cactus contain an Hankel. Can you say in this range?
I mean, these are cubics, so
well, for cubics, it fills almost right away because it's only 2-1 split.
Right. There are not many catalepticus.
So n
fills
it in.
So when R is even here, does it mean, or when in the other case, it means that you will get, generically, you get just one local scheme?
Yeah, the one local scheme that computes the Cactus rank, yeah.
For the R even and odd.
Yeah. For the R even. For the R odd, you have to use the quartic, whose cubic tails is F on one point, yeah.
Is there a good description of that special point? Some point.
You mean of this even and odd thing? No, I mean, I tried to find a good explanation, at least for myself, but I mean, it turns out from the proof, but I don't have a deep understanding of this phenomena.
Other questions? Okay, Alessandra again.